In this video, we are going to look at the most famous equation of them all, Einstein's energy mass equivalence formula, E equals mc squared. And we're going to have a look at some of the consequences of that. But basically, simplifying what this equation is telling us is that energy can be converted into mass and mass can be converted into energy. Now, strictly, the full form of Einstein's equation actually looks like this. E equals p squared c squared, where p is momentum, is m squared c to the power of 4. That's the full form of Einstein's equation. Now, why am I telling you this? Because we're going to need one of the outcomes of this in a little bit. So where you've got particles which are not moving, so in other words, we might call that rest mass. Particles that are not moving have no momentum. So that first term disappears, and so we're left with E squared is m squared c to the 4. Okay, now we square root it and we get equals mc squared. But equally, particles with no mass, i.e. photons, that final term disappears, doesn't it? M is 0, and so we're left with E squared is P squared C squared. In other words, things with no mass do have momentum. Interesting idea. So photons of light have no mass, but they do have momentum. Okay, so a little bit of kind of off spec, but we're going to pick up on that idea in a short while. Okay, let's talk about this energy equivalence of mass then. Okay, if we've got something like an electron, it has a rest mass of 9.11 times 10 to the minus 31 kilograms. There is an energy equivalence of that mass. Okay, in other words, if we could convert all of the mass of an electron into energy, how much energy it would have can be calculated from Einstein's equation. Okay, so mass is 9.11 times 10 to the minus 31 kilograms multiplied by the speed of light squared, and we get 8.2 times 10 to the minus 14 joules. We often express this in electron volts. And so if you divide by 1.6 times 10 to the minus 19, you get 0.512 mega electron volts. Okay, try and remember that number. We're going to refer back to it in a minute. The mega and the giga electron volts are common prefixes to use when working with particles like electrons and neutrons. Okay, so that is the energy equivalence of the mass of the electron. Now, it is the rest mass of the electron. So that's the equivalent amount of energy for an electron at rest. If the electron happened to be moving, it would have mc squared and also a half mv squared amount of energy. Okay, right, let's look at some consequences of this mass energy equivalence. Firstly, let's have a look at the consequence of mass being able to be converted into energy. Okay, and we're going to give this a name. We're going to call it, great name, we're going to call it Annihilation. Okay, the clue's in the name. We are taking all of that mass and we are seemingly destroying it. Obviously we're not. We are converting it into energy. So the mass of those particles no longer exists. It now exists in the form of pure energy. So what do we need for this to happen? We need a particle and we need an antiparticle. Now, if a particle meets its antiparticle, annihilation happens almost instantaneously. So if you meet your counterpart, your anti-person, do not go anywhere near them, because if you shake hands with them, you will annihilate each other and you will go up in a flash of light. So we're going to get two photons being produced. Okay, so we've got a particle meeting its antiparticle. All of that mass gets annihilated and it's converted into energy. So how much energy have we got? Well, we began with mc squared amount of energy associated with the particle and the same amount of energy associated with the antiparticle. Okay, remember the only difference between a particle and an antiparticle is its charge. They both have the same amount of mass, so therefore they have the same energy equivalence. We've got 2 photons. The energy of each photon is hf. Now, for this to occur, we have to obey some conservation rules. Conservation of momentum is the first one that we have to obey. And if we consider this from a vertical and a horizontal perspective, because we've got both forms of motion present, then we can see that it's conserved. Okay, let's consider horizontal momentum. The particle and the antiparticle, because they have the same mass, have the same amount of momentum, but in the opposite direction. Okay, so the sum of the momentum of the particle and the antiparticle is 0. So therefore, if we sum the momentum of the photons, remember what we said earlier, photons have momentum, that also has to equal 0. And if we consider the motion of the photons horizontally, there is no component of their motion horizontally. It's pure vertical motion. So horizontally, momentum is conserved. Okay, what about vertically? Well, the particles have 0 momentum vertically. They're only moving horizontally. So we've got 0 vertical momentum from the particle and the antiparticle. So what about the photon? Well, they are moving in the opposite direction. Okay, so if we sum up the momentum from the photons, they have an equal amount of momentum, but in the opposite direction, and so they add to 0. So whether we consider this vertically or horizontally, momentum is being conserved. Right, what about conservation of energy? Right, what's the energy at the start? It's the energy of one of the particles and the energy of the antiparticle. And what's the energy at the end? The energy of 2 photons. In other words, we've got 2 lots of mc squared because the energy equivalent to the particle and the antiparticle are the same. And we've got 2 photons. So in other words, the energy of the particle is equal to the energy of one of the photons. Okay, now we could go on to work out the wavelength of the photon that's produced using our wave speed equation. Okay, so let's have a look at an example and let's use the neutron as an example. So let's look at neutron annihilation. So there's the neutron, there's the anti-neutron, there's the photon, there's the photon. We need to know the rest mass of the neutron. So you look this up in your data and formula booklet. There it is. So let's work out the energy equivalence of the neutron. mc squared 1.675 times 10 to the minus 27 multiplied by the speed of light squared, and that is 1.503 times 10 to the minus 10 joules. And if I just divide that by the charge on the electron, 1.6 times 10 to the minus 19, I get 939 mega electron volts. Okay, remember the energy equivalence of the electron was half a mega electron volt. So that difference in mass gives you an enormous difference in energy equivalence for the neutron. Okay, the question is then what frequency of photons are being produced? Okay, well, the neutron produces one of the photons, or sorry, the energy from the neutron produces one of the photons, and the energy from the anti-neutron produces the energy for the other photon. So therefore, the frequency of the photon is equal to the energy of the neutron, and I've got to use the value in joules, not mega electron volts, divide it by Planck's constant, and I get a frequency of 2.3 times 10 to the 23 hertz, which is a very, very high frequency. So let's link it to the electromagnetic spectrum. What's the wavelength of that photon? 3 times 10 to the 8 divided by 2.3 times 10 to the 23, and I get a wavelength of 1.3 times 10 to the minus 15 meters. Where is that sitting on the electromagnetic spectrum? It's in the gamma region. Okay, so when a neutron annihilates itself with an antineutron, we get 2 gamma photons produced. Okay, that's mass into energy. What about the reverse? Energy being converted into mass. Okay, we've got a name for this, a bit less exciting. It's called pair production, but the clue is in the name. Okay, so what do we need? We need a photon. We need a big nucleus. More on that in a minute. And if we've got a nucleus nearby, we get a particle. And that's going to have an energy equivalence of mc squared. And we're going to have an antiparticle. And that's also going to have an energy equivalence of mc squared. Okay, so that photon energy has to be sufficient to create the particle and also the antiparticle. Okay, so in other words, that HF joules of energy that photon needs to have needs to be at least 2 lots of mc squared, because we've got 1 photon producing the particle and also the antiparticle. So let's have a little look at one of the most common examples of pair production, and it's the electron-positron. And the reason for that is the electron and positron have the smallest mass, so it requires the lowest energy of photon to produce this pair. So there's our incoming photon. It's near a big nucleus, so we get our electron and we get our positron being produced. Okay, so the energy of the photon then has to be at least as big as mc squared plus mc squared. In other words, 2mc squared. Okay, so we could express this in this way. The minimum energy of the photon has got to be at least 2mc squared. Okay, now we can relate this again to frequency and to wavelength. So 2mc squared has got to be equal to, what shall we do first? Let's do frequency first. So the minimum frequency is going to be 2mc squared over h. Okay, why is it the minimum frequency? Because if you think about your photon equation equals hf, energy is directly proportional to frequency. So the minimum energy corresponds to the minimum frequency. However, let's talk about wavelength, because there's an inverse relationship with wavelength, isn't there? So we've got that. So we get rid of one of the c's. So in other words, wavelength, but it's going to be the maximum wavelength, is 2h over 2mc. Okay, why is that? Because there's an inverse relationship, isn't there, between frequency and wavelength. So if you make the wavelength even bigger, then the energy of that photon is going to be smaller. Okay, so it's the minimum frequency, but the maximum wavelength. Okay. Now, is momentum being conserved is the big question. The diagram seems to suggest it's not. Because in the diagram, I've got horizontal and vertical momentum. And it looks like they're not being conserved. So the missing part of this is that this only occurs near large nuclei. And so some of the momentum of the photon is transferred to the nucleus. And although the nucleus doesn't move very much because it's got such a huge mass compared to anything related to it, it's actually able to carry a significant amount of momentum. Okay. Now, is it possible then to do this kind of pair production? Is it possible to get two photons interacting and forming two higher mass particle and antiparticle pairs? Yes, in theory. But in practice, it never happens. And the reason for that is how do you get two photons arriving at the same place in time? That's an extremely unlikely event to happen. So while in theory it is possible to get multiple photons producing a particle-antiparticle pair, it's exceedingly unlikely. Okay. Now, how do we all know this is actually real and this is true? If we have a look at the diagram in front of you, that's what we call a cloud chamber. We're firing in from the top a photon, a gamma photon, and it's ionizing the gas within the cloud chamber, and it's leaving an ionization trail. It's leaving like a vapor trail in the same way that an aircraft leaves a vapor trail in the sky. And we apply a magnetic field. And we're getting that circular motion that we know is associated with magnetic fields, but we're getting two particles produced and they are spiraling in opposite directions. So the way that we explain that is they must have opposite charges. So that's good evidence for the particle-antiparticle pair being produced. Now, the reason that it's spiraling and not moving in pure circular motion is because as the particles move through that gas chamber and they ionize the gas, there's that transfer of energy. So the energy of those particle-antiparticle pairs is decreasing over time. And so it's not uniform circular motion, it's kind of spiraling inwards and eventually all of that energy goes. Okay, so that's a little bit then on the significance of Einstein's E=mc² equation. You now need to practice some calculations for annihilation and for pair production.